Smart pointers. Turns out I'd accidentally deleted some slides from the resource management one, and it was meant to be part of that lecture. Do you remember at the end of week 5, I was like, there's something missing. And it was meant to be in the course, but I think in all my restructuring and rewriting this time, I just accidentally knocked it out. But it's a fairly short piece, but it is really important because we use it in assignment 3. Has anyone looked up a smart pointer before or seen it on their journey? Cool. What is a smart pointer then? It handles the pointer, has ownership over the pointer. I think that's accurate. We can unpack exactly what some of that means, because some of that language is hard, right? It's hard to describe these things. So we talked about in a previous lecture that heap memory, or what we call like unnamed memory, right? Unnamed memory and heap memory are the same thing, are dangerous, as there's always a chance that the resource isn't deleted. The reason we call it unmanaged is because the software is not managing it. You are managing it as a developer. So we need solutions to help with this, and we use smart pointers to look at that. So recap on object lifetimes. We talked about that last time. Maybe I'll cover it again. So if we want to create a safe object lifetime in C++, we always want to attach that lifetime to the lifetime of something else that's a named object. What that means is that ideally, we have an unnamed object, which is a heap object, and we somehow tie it to a named object, something on the stack, if we can, so that that stack object can manage itself. What I mean by that is, like, when you go and create a vector, the objects that are created within a vector themselves are in the heap, right? But the vector, when you create it, is a stack object, and therefore the vector's managing it. You don't have to worry about it. So when you come along and you go and do your whole, like, there's your code, and you say, yep, auto v equals standard vector int 1, 2, 3. Even though that's using the heap, there's heap stuff going on, you don't care because it's behind a stack object. Because v's on the stack, and therefore when v goes out of scope, it will be destructed, and that's delegated to someone else. So stack objects or named objects are great things for us, and we want to use them to protect us from these heap objects. There's this principle called RAII, or Resource Acquisition Is Initialization. I'm not a huge fan of how this is described because I think it makes it sound scarier than it is. But basically, it's just another way of saying what we said before, which is like, well, I'll come back to that slide. I think it's going to make more sense once we talk about some practical bits. So let's have a look at a pointer, and we want to make a pointer safer. So this particular code example, let's imagine you have a class called myIntPointer, right? I know that text is quite small, and I'm sorry that I can't turn these bloody lights off. Maybe I can paste that into an editor and make it a little bigger for you. Let me put it in a C++ file so it looks a bit better. Yeah. Great. So we have this class called myIntPointer, and it's got a constructor, and the constructor takes in a pointer to an integer, and that initializes the pointer to an integer that's stored privately in it called value, and you can get that value, and when there's a destructor, it calls delete on that. This is basically the principle of resource acquisition is initialization. This is the principle of the object lifetimes I mentioned. This is the principle of smart pointers. If you can understand the value of what we're doing here, you understand pretty much everything else that's coming, which is that we think when we create a new integer like this, because we've created this unnamed memory, this heap object, which is now dangerous, we say, actually, I'm going to give you to something called p, this named stack object, which is of this type. You are now looked after by it. And we delegate that worrying about it to the stack object. So now we don't need to free it, we don't need to worry about it, we just leave that to the stack, because eventually myIntPointer will go out of scope down here, and its job is to delete the underlying pointer. So no freeing involved here by like us who's using it. So super, super handy, because the alternative would just be to like, work with this pointer ourselves, but then we'd have to free it. So we've kind of protected ourselves because it's tied to the stack now, just like that vector example I gave. No deleting here at all. It is a very light abstraction. Yeah, and Tim's written on YouTube as well, like, I think this is the main scenario where we would have a non-default destructor. Yeah, so in the context of this course, there's not really a reason for you to define a destructor in the limits of what we're doing. The main time to do it is if your object itself is managing heap resources, and therefore it needs to free those heap resources. Because there was a question, if I use default for the destructor, will it default it automatically? I love this question because it makes you think about what's going on, which is that it doesn't always do what you expect. What it does is it frees up this value here, but that is just an 8-byte piece of memory that points to an integer. That's what value is. It's not it's not the thing it's pointing to, because obviously P is on the stack and it has a certain amount of space. So you're only like popping off the pointer, not what the thing points to. And this gets tricky because of how we talk about stuff, you know. Like we say, oh, you know, what's value? Well, value is a pointer to something. It's not the thing it points to, it's itself a pointer, and like the words can be messing up. But so yeah, there is a default destructor here that you don't see happens, which is that it also kind of like frees up the stack object value. But that goes on all the time in all of your code. We just never talk about it, right? Like the idea of popping off the stack is so automatic in our high-level programming, in every language you probably programmed in, you know, at uni, that you don't even think about it most of the time. So the default constructor does get stuff off the stack. It just doesn't touch the heap, because that's a pointer to a heap thing. So, okay, that's how we make a pointer safe, which kind of comes back to this thing here, which is saying resource management is about emphasizing that you acquire as you initialize stuff. And what that means is that when you create something in C++, like you do a new array, a new object, at that moment that you create the new thing is the same moment that you should wrap it in something that looks after it. You know, so it's really common practice that you never have a stray new. A new is always part of a stack object, and that stack object is managing it. That's that principle that we're talking about there. Now, smart pointers are ways of wrapping these unnamed objects in named stack objects, so that lifetime is managed really safely. They're a great concept. They were introduced in C++ 11, which was kind of the main revolutionary part of C++. They have some quirky little properties relating to ownership, but we'll kind of loop back to that slide in a bit. For now, it's more just focused on the fact that there are these smart pointers. They look after heap objects. Hopefully we got ourselves a simple example here. Actually, maybe I'll just start with where is this? Oh, 5.3. Yeah, sorry, I'm doing 5.3 at the moment. Let me just copy that out and start with something really simple. Just start with that piece of code there. So, cd build make unique. Hope it works. It's probably going to say no. Oh, good. There you go. So this, and you know, maybe I could make this like new int 4 or something. That might be better. I don't really know how that works otherwise. The unique pointer is behaving a lot like that type I mentioned before, that myInt pointer type we created, where it is, it's a templated type like vector. It says I'm going to take in an int, and you give it a pointer to that, or you know, you give it a pointer to that int, and it stores it, and then when it goes out of scope on line 6, it will free that for you. So this has no memory leaks. And if you're not sure, I find memory leaks when programs end a little bit confusing, because when any process ends, all the memory it had's gone anyway, you know? So this program wouldn't leak memory, but maybe a better way of explaining it is, let's imagine that I had a function, void do. It's a pretty silly function here. And all it's going to do is create a unique pointer of, int 4. And then all I do here is say while true do, like this, right? This program would not leak memory, because every time this function's called, the scope starts here. I create a new int, but it's captured within this named object. That goes out of scope on line 6 when the function wraps up, so it frees that underlying heap object, and the function comes back, and then the while true goes again. So it's constantly creating these little ints and then freeing them really rapidly. Whereas, for instance, if I just kind of here said like int star, u equals new int 4, like this program would leak memory. As it loops, it would just get bigger and bigger until it probably like crashes the computer, right? If you've never done it before, I'd recommend you write a program like that. It's quite fun to just like see what happens. I don't want to do it here because I'm streaming, if that makes sense. I don't want to like kill the stream. But it's quite easy because you would just make it, you just make one file's fine. And then, what's it mad about? Expected unqualified ID. Oh, I'm using a reserved word probably. That's probably it. Unused. Yep. Cool. And then all you would do is you would just run 5.3 unique like that. And that will start chewing up memory on the computer, right? If you're not sure how to check memory, you can just, I'm not on Linux. Does anyone know how to check memory on a Mac? I only really do it on Linux. You can do it on the CSE machine, though I imagine they get mad at you because it's shared resources. I always tell people this story. It's like one of my earliest memories with programming. It's like a long time ago. I'd figured out that there was like a function I could write on the server, and it was just like an email function. And if I just put in like an email address and a subject and a body, that I could write a function and run it, and it would send an email, which was like the most mind-blowing thing to me, that I could just send it. So I thought it'd be funny if I just like put it in a while loop, and I just like put it in this like while loop with like 1 million emails, and I like just sent it to my sister, and I was like, this will be funny. I'll just like jam up her inbox with like 1 million emails of something. And she was screaming at me and kicking me, and we got like, it was like stopped at like 32,000 emails, just like randomly stopped. And I kept trying to send more and it wouldn't. And then like a day later, I got an email from like the hosting company that was like hosting the thing, and they were like, can you never do that again, please? You crashed our server. So I'm pretty sure a similar thing kind of happens if you try on VLab to like do something like this. I imagine eventually you would probably kill a few people's sessions or give the server hassle, and at some point someone in the school would like be like, that user account seems to be doing this quite a lot. I don't know what top is. Oh, okay, it's just showing me like, where's the memory? There we go. Yeah, so if I run this command, and I want to be careful with it, it will unique. See? Look. Oh, God. I don't know if you caught that. Did you catch it? Do it one more time, all right? This is completely a rabbit hole that doesn't matter. Watch the memory thing. OBS, the streaming software, is using a lot at the moment. You will see this program called Unique very rapidly appear to the top. I have 32 gigabytes of RAM on this laptop. OBS is using 1 gigabyte of it, right? So when I run that, you'll see Unique just kind of appears and then appears and then appears. See, it's just like sucking up RAM like that. So that'll eventually grow until the operating system, if it's a good operating system, will kill it. Point of all this stuff is memory leaks are bad because they don't normally happen that fast, because no one's writing while true loops that are just mallocing something for no reason. But if you have memory leaks in your program, it will go wrong. So we have these unique pointers, whereas if I run it like this with a while true, because the stack object is managing it and going to be freeing it, hopefully. What is it doing? All right, I didn't make it. Every time I do one JavaScript lecture in the morning, I forget how to write compiled languages. It happens constantly. So hopefully this one doesn't. Yeah, so it's using not very much. Like that's a K, not an M. So it's saying it's using 1 megabyte of RAM basically to run right now. Because it's constantly freeing the memory because we gave it to the stack. We didn't free anything ourselves because we have this great tool that manages it for us. Excellent. That's lots of fun. Thank you, Tim, for your top comment. That's a funny pun, actually. Okay. So now we have a look at a unique pointer. Where a unique pointer is special is that it's not just a benign wrapper for a pointer, but it makes sure that no one else is able to point to your unique pointer as well. What I mean by that is that if I just keep this code really simple, this code will not compile here. It doesn't compile because a unique pointer doesn't have a copy assignment and it doesn't have a copy constructor. The reason for that is because if you think about it, I'm a unique pointer and I'm pointing to this unnamed unnamed part of the heap, like a heap resource over here. And my whole job is that when I go out of scope, I need to free that resource too. So the tricky thing is if someone was to copy me, so I'm over here, and then someone's over here also pointing to that same resource, once one of us goes out of scope, they're going to free the resource, and the other one's going to be left pointing to something that's been freed, right? So it makes sense to have like unique ownership over this thing, because having two people who are ready to like kill the thing as soon as they're gone is just going to create chaos. So the way that they go and implement that is, think about our previous knowledge, they actually delete the copy constructor and copy assignment in the class definition. So we've talked about that before, as like somewhere out there's like a class called unique pointer, like this, and they've got like unique pointer that takes in like a const reference to a unique pointer, something like that, const unique pointer reference, other, and they just delete it. That's how they do it. It's nothing more than that. Like, this is just libraries that people have written. They delete the copy constructors, they delete the copy assignments to make sure that people can't play with it. So there's no copy constructor, no copy assignment. So those two lines of codes, if I comment them out, will not work. However, there are ways to kind of distribute things between it. So there is a function on a unique pointer called release. And what release does is it basically says, we can look this up in the documentation, right? Standard unique pointer here. And you'll see it doesn't have many methods. They're very simple things. They have release, reset. So release returns a pointer to the managed object and releases the ownership, and reset replaces the managed object. So this is basically how you would transfer it from one unique pointer to the other. I'd never have really done this before. It's just like not something that I find super common, but it paints the picture that you can't just make two things equal. You need to find a way to, this is saying, okay, so what release will do is this function call will return a pointer to that int that I created up the top. And then .reset for UP3, it will kind of delete and reset what it had and track the new pointer, which is the original int for UP1. One thing is, as well, is that we also have move semantics for our unique pointers. So we don't delete the move constructor. We don't delete the move assignment. They exist because they make sense in this scenario to be able to like move an object from A to B. So this would be like the more natural way that you would do it, is you would just move it like that. You don't need to do this kind of complicated line. This line does work, but it's just unnecessary when the move exists. If you want to get the underlying pointer, then you call .get on it. And if we have a look, .get will return a pointer to the managed object. So that will return a pointer type in this case. And then you can naturally dereference the unique pointer, and it will give you the thing. And this actually this is where it's really useful doing assignment too, because you can start to understand how this is implemented now, because in that unique pointer class, someone has just come along and overloaded the dereference operator. And that's the multiplier operator. How does the dereference operator work? I don't know. Can't remember. It doesn't matter. It's like they have a dereference operator, and all they do is they overload it to like, because somewhere in here, right, they've got their like, int star underlying pointer, right, that they're managing, or you call it like the unnamed memory. It could be called anything you want. Is all that does is simply returns the dereference of the underlying piece, right? So when you dereference the unique pointer, it's just like passing that through and grabbing the thing underneath and dereferencing that and pulling it back up to you. So they're very, very, very lightweight abstractions, which is quite cool. Makes sense? Yeah. Cool. Yeah. Good. Exciting. So with unique pointers, sometimes we would like a second variable to point to the thing the unique pointer is managing. That happens. Maybe we want to like pass it into another function or something. In those cases, you actually can use raw pointers. It's one of the few instances where I'm trying to just get clarity here. UP1, OP, yeah, okay, cool. So if we look at this code here, this observer code, OP1 is actually a raw pointer. Like it's a real raw pointer, those things we tell you not to go near. And it simply says, hey UP1, what are you pointing to? I would like to point to it too. So UP1 is a unique pointer object, this lightweight abstraction that stores a pointer to the unmanaged memory inside of it. And OP1 here is literally just a C-style pointer that's pointing to that unmanaged memory too. So they're both pointing to it, but only one of them owns it. So UP1 here is like the owner of that, and OP1 is just like an observer. So the reason we call them an observer is because if OP1 goes out of scope, nothing happens to the underlying memory. You know, it doesn't own it, doesn't track it, it doesn't manage it. But that's important because, as I said, you can't copy a unique pointer. But just because you can't copy it doesn't mean you don't need other things to point to it too. Observers are kind of just an easy way to deal with that, since you can't copy it. It's one of the few instances where we say, like, okay, raw pointers are fine to use. You just kind of got to use them sparingly. There's a bit more detail here. Unique pointer owns the object. When the object pointer is destructed, the underlying object is too. Yep, unique pointer may have many observers. There is an appropriate use of raw pointers. This isn't appropriate. That's poorly worded. Once the original pointer is destructed, you must ensure you don't access the raw pointers. So this is where you actually just have to be a good human again, because once you have, like in this case, reset the unique pointer to point to null, because if you reset a unique pointer and you don't give it anything, it's just going to point to null, right? It's like default state. You can't do this again, and nothing's going to stop you doing that last line there, except you as a programmer have to write code to prevent that. So whilst these things protect us a lot, they don't stop you actually accessing the underlying pointer, having something else point to it, and then calling that after it's been freed. That just needs some degree of discretion. Obviously, if I go and compile this one and then run it, it will kind of work, right? Yeah, so this actually is perfect because, you know, we created a 0, we set that to be 5. Unique pointers, like, this is the cool thing about a unique pointer. You can treat it like a pointer, you know? Like, that's just me using it as if it's the object itself. So really handy. I print that out, I get 6. I get an observer. I then use the observer to change it, right? We say observer, but we don't mean that it can't use it to change anything. We just mean it doesn't own it. Call it a non-owning pointer. Might be another way to think about it. But then once we reset it, we try and print it out again, and we get gibberish because it's still pointing to that memory address, but we already freed what's there. So we're just getting crap. Like, it's probably used by the stack for something else at this point, for some other number. Yeah. OP1's a stack object, so you could try and free what it points to, which I know is what you mean. Just like clarifying that. Yeah, I mean, let's try it out. Delete OP1, because OP1, yeah, you give it the pointer to the thing. Oh no, pointer being freed was not allocated. Your whole program crashed immediately, and you lost your job. You know, I don't know. It's like this case. It's because we already freed it. We can't free it again. It's like a double free error.
What if it's before the reset?
Oh, now we're really having fun. I imagine we'll have the same result. It's just who freed it will be different. Yeah. So in this case, I think what's happened here is like it's the unique pointer's gone to free it as it expects. It's like, it's my job, time to free it. And then the whole program just crashed because you already went and freed it yourself with the observer.
What if you don't reset it?
Oh, if you don't reset it, well, exactly, because why do we need to? Oh, you don't. This is just like a playground of code, yeah. But I actually love where that might be going, because if I reset it, you still have the same problem because the unique pointer is doing its job, which is when it hits line 14 here, it goes out of scope, frees the thing underneath itself. So observer pointers, like, you would never use an observer pointer to free. You'd never free an observer pointer. It's just observing. That's a really easy thing to just never do. In general, your code you write should avoid delete in it, in like the functional part of it. The harder part is knowing to like not try and print it or change it after that point. Yeah.
Can you explain the nuance between an observer pointer and a copy of a unique pointer?
So the observer pointer or just the raw pointer, so that like, you know, no one's too confused. It's just because like since you can't copy the unique pointer, but you might need someone to point to it, you use that. Because an observer pointer or a raw pointer is just pointing to it. It just doesn't own it. Yeah, it's not reference counting it. It's not, you know, responsible for freeing it, really. Most of the time, though, that's not really a big deal. You can just kind of use a unique pointer. There was this table we kind of talked about at the start, which is like a unique pointer it takes ownership of the underlying resource, but it doesn't share the ownership. It won't copy. A raw pointer doesn't take ownership, and it can't share ownership either. If you can't take ownership, you can't share ownership. Which brings us to the next couple of things, which are our shared pointers and our weak pointers. Just when you were feeling like you were on top of it. Oop. I decided to throw this slide in between, looks like. Oh yes, a random point. We can use another function to actually remove the new keyword altogether. This is pretty cool. I'll bring the code up just so it's a little bit bigger. Here, you can obviously go and make a unique pointer to a string, and then you can go new standard string hello. This line is fine. The downsides with this line are that the OCD types obviously aren't going to love the existence of new in that line, because new and delete are kind of bad. By principle, there's a philosophy that you should try and avoid them wherever humanly possible, because then you're touching, you know, heap stuff, which is dangerous. Also, there's a bit of repetition there because you are specifying the type of the unique pointer, and then you're also constructing that object there. So the people that manage the unique pointer library, they also created this function. I believe it's a function. I don't believe it's a class, because unique pointer, you're obviously constructing a class there. I should check I'm right about that. Maybe I'm wrong. Oh, it looks like a function. It's a templated function. Sure. But it's a function that literally just takes in your variable, the data. It then goes and mallocs it, and then it passes it into, you know, a newly constructed unique pointer object, and then it just returns that. So it's just, again, and it's another lightweight abstraction for this line here. So these two lines do the exact same thing. One of them just does it a little bit shorter. So this one's very handy. So when you create a new unique pointer, you'll typically use this line here, nearly like every time. There's no reason to kind of go do this thing up here. Cool. Shared pointers. This stuff gets maybe a little bit more complicated. A shared pointer is really similar to a unique pointer in so many ways. It's just that it's happy to share ownership. What that means is you can copy it. You can copy assign it, you can copy construct it, totally fine, no issues. And the rule is not that when, because with a unique pointer, it's like when the unique pointer goes out of scope, it frees the underlying object, right? With a shared pointer, it's once I'm the last shared pointer to go out of scope, then we free the underlying object. So if I'm a shared pointer pointing here, and then I have a friend here pointing to that same spot, another friend on my right pointing to that same spot, it only gets freed when, for the three of us, the last one goes out of scope. So if I go out of scope and then the person on my left goes out of scope, it's still okay, but it's when that last person on my right goes out of scope, they're like, oh, I'm the last one, better free that object. It's really useful. I'm trying to remember, we wrote it down somewhere in the slides. Sometimes it's really tempting because you think, oh, I have different parts of my code that need to like point to this thing, so I'll use a shared pointer instead of a unique pointer. But the rule for shared pointers is that you should use shared pointers when you don't know which variable will go out of scope first. If you know, like if you have, you know, those three people I just mentioned, like A, B, C here, let's imagine you have three things pointing to one resource. If you always know that like Hayden is going to be the last one standing, then you just make Hayden a unique pointer and you make the two others observer pointers. That's the kind of thing. But if you have three and you're like, I just don't know which one's going to go out of scope, then you would, yes, just make them shared pointers as well. The good thing is these are relatively easily refactorable ideas, so it's not like you can like screw one up and it screws you forever.
How would you like not know which one is correct?
That's a good question. I think one example, and this actually ties into your third assignment, because your third assignment is a graph. You have to go to make a graph in C++, very complicated graph. But let's imagine that you have, I think the example was like, I'm going to butcher it a bit, but like you imagine you have a node, and that node has like edges going into the node. If your edges are all kind of pointing to the node, right? You've got edge 1, 2, 3, 4, north, south, east, west to that node. Each of those might have a shared pointer to the node itself, right? Because as you're adding and deleting edges to that node, you don't know which edge will be the last edge standing. So you delete this edge and this edge, and then it's only once that last edge is gone and that node is not pointing it, not connected now, you just delete the node because it's unlinked to anything. That's kind of an example. The thing is with shared pointers though, is they come alongside these things called weak pointers. Weak pointers are used with shared pointers like observer pointers. They're used when you don't want to add to the reference count, if that makes sense. So they're used when you kind of want to observe that pointer, but you don't want like the observation of that to block the deleting of it. It's really just a lot like raw pointers. The reason we have weak pointers though is that they make, I think I have another example with weak pointers. So let's just start with the shared pointers and then we'll come back to weak pointers. So if I look at the shared pointer example, X is I make a shared pointer for 5, and then Y is we do, why the hell do we do that? I don't see why we do that. Why are we doing that? Oh, we're copying it, sorry. Silly me. So I think it's a bit of a weird way to write it, but okay. Yeah. So X is, we create a variable called 5. So 5 is an int, make shared like make unique. X is now a shared pointer that points to a heap object that is an integer 5. When we say Y equals a shared pointer and we give it a shared pointer, it's standard copy construction. So we now have a shared pointer X and a shared pointer Y. They both point to that 5 in the heap. Okay, so they've got a reference count of 2. When I run this, let me just get rid of some lines so we have less distractions. Make shared. Cool. 5.3 shared. Does anyone here watch F1, Formula 1? No. I'm only just starting to watch it. I watched it last night. It's like one of my first. Anyway, I'll go talk to myself later. So we got use count here. You see we got 2, X and Y, right? The use count's 2, because even though X is one shared pointer, when I print out use count, that's like how many of us are pointing to that heap object. So 2, right? Because we have X and Y. So each shared pointer is aware of how many others are pointing to it. And then if I print out the like dereference X, if I dereference the shared pointer, it's like dereferencing the underlying type anyway. Okay, cool. So then what happens if I reset X? Well, nothing interesting is going to happen yet, but the use count will change, right? Because it's 1, because I reset X, I basically freed X, force freed it, but the value's still there when I access it with Y. What happens if I try and access it with X? Segmentation fault. I didn't actually expect that to seg fault. It's probably dereferencing null, I'm guessing. Because when you like reset a shared pointer or a unique pointer, I'm pretty sure it just points to null, like as a placeholder, because it's got nowhere to point. Could be wrong. Let's see what happens if I print X by itself. Well, that's going to give me the actual that's not going to work. Anyway. Maybe the address of X? Should probably stop playing around. I don't know. That's probably just the address of the shared pointer. Point is, once you reset something, right, you shouldn't be using it. But when I Y reset now, because X has been reset and Y was reset, it was the last one tracking it. Therefore, it should now have a use count of 0. And if I try and print out the value, which I shouldn't, I'm going to get problems again, right? So you shouldn't be calling, like, you shouldn't be dereferencing the value after it's all been freed. But the main point here with the shared pointer is that the object stays alive until the last one pointing to it is gone. Did I lose my camera? Okay. Yeah, any questions about that? So again, it got deleted here on line 13. If I didn't have this X reset here, it wouldn't have gotten deleted on line 13. It would have instead gotten deleted on line 17, which is when all the stack objects went out of scope. Now, if I have a look at this other example with weak pointers, on line 5 here, I'm making a shared pointer to a heap object 1. So just the int by itself 1, cool. And then I create a weak pointer, and what you do is you give a weak pointer a shared pointer itself. So a weak pointer is constructed by a shared pointer. And the best way is you just got to think of a shared pointer. You just think of a weak pointer like it's a shared pointer that doesn't contribute to the reference count. One interesting thing that a shared pointer does have, though, One interesting thing that a weak pointer does have, though, is it has this function called lock. And what lock does is lock creates a shared pointer from the weak pointer temporarily, and it's typically used temporarily, because here's kind of the dilemma, right? Remember, a lot of code, and even C++ code too, it can run concurrently. You don't do a lot with concurrent programming at uni, right? I'd say it's like one of the things that uni's not particularly great at teaching people. And what that means is you got to remember that if you're running these big systems, there might be many threads of C++ running at the same time or going on, and you might not even know when things are going to end, because you think, oh, well, I could just use the weak pointer here, right? Like, let's imagine for a second that you just, like this, right? You're just like, yeah, WP, dereference it. That should work. Make weak. Indirection requires pointer operand. Surely not. Can you not even do that? I thought you could. Well, there you go. I didn't even think you couldn't do that. So the point is, like, let's imagine for a second that you had that. The reason this is particularly dangerous is because you just don't know if it's going to exist right now. You know, it's like, because somewhere in another thread on the computer, the shared pointers could all go out of scope or something like that. In this particular case, it's okay because you can see X is alive here, right? Sure. But what happens if it got passed into you? The weak pointer was given to you. So the way it works is, like, at this line of code here, the reference count is 1. Okay. But to make sure that the reference count doesn't go to 0 whilst you're using it, what we do is we call this line here, and what this does is this returns a shared pointer. So as of this line now, the reference count is 2 for a moment. See a few funny got some real squinty looking faces at the moment. And then what we do is we try and see if y is not equal to null. So basically, a weak pointer, think of a weak pointer as like, the way I like to think about it, it's like a dormant shared pointer, right? So like you have shared pointers out here, and you might have a weak pointer that is kind of sharing that shared pointer. And it's just existing, and if all the shared pointers go out of scope, the weak pointer's gone too, you know? It's not blocking the deletion of anything. However, at some point, if you want to use the weak pointer, it's got to kind of get a clasp on something so that it doesn't get freed halfway through its use. So what you do is you kind of lock it in for a second, and locking, the simplest mechanism for that is that y is now a shared pointer itself. So y is a shared pointer, but you also don't know at this point if everything's gone out of scope. Because maybe by the time you've called this code, all the shared pointers have gone out of scope. So your weak pointer pointing to that shared resource is like gone, you know? So what happens with this lock is that returns a shared pointer. Y is a shared pointer to the 1. But we need this line here because if all the shared pointers have gone out of memory, you can't lock anything, right? It's gone. The weak pointer, which was pointing to this thing that wasn't stopping anything being deleted, it didn't stop anything being deleted, and it all got deleted. It's not there anymore. So you need to check if it's not null. And if it's not null, then you can use it. then you can treat it just like a shared pointer. And then what's cool, I mean, you know, maybe you'd wrap this in like a scope or something. You can do anything you want. Is like, maybe I can show you that. That'll maybe clear this up a bit. Is like, then as soon as you're done with it, what happens here? You hit line 17, 18, y goes out of scope. Y is a shared pointer. Okay, so the shared pointer goes out of scope. And this works in a bunch of scenarios, because if there was already a reference count of 1 before you used it, whilst you temporarily got a lock on it, you created a new shared pointer, and the reference count's 2. Okay, you use your thing, and then you're done with it, and you delete your little temporary shared pointer, so the reference count goes back to 1. Okay, cool. Well, what happens if the reference count was 0 before you even use the weak pointer? Well, you get a lock on it, it creates a shared pointer, but because this thing's long gone, your new shared pointer just points to null, so you don't even get inside your if statement there. Okay, and then we have another scenario. You have a shared pointer already, cool, you've got a weak pointer pointing to it, you do the lock on it, so now the reference counts 2. So on line 13 here, the reference counts now 2, because you've created your temporary shared pointer. Well, imagine in another thread on the computer, the only other shared pointer that you have it to it goes out of scope, right? So this one's gone now, you're just left with this one, right? Stop laughing. It's like you're left with this one. So just for that brief moment, whilst all the other shared pointers have gone out of scope, because you got a lock on it, you can use it for a second, and as soon as you're done, and your temporary shared pointer goes out of scope, then it gets deleted. So it's just like a very confusing but elegant way to say like, hey, don't delete this resource until everyone's done with it. And all a weak pointer is the pointer you use where you're okay if it gets deleted, you know? I know these are really simple examples, so it's like hard to make them feel kind of concrete and relevant, because they're very like little mini academic pieces of code. But you know, let's imagine that graph example again. It's like maybe you want a weak pointer to a node. You store that somewhere, like you store a list of nodes, right? So imagine you have a graph and it's just a bunch of edges, and each edge points to nodes, and they all share like linking to that same, the same node. Like if you've got 4 edges coming into a node, right? They're all going to be shared pointers to that node. Well, maybe somewhere else in your code, you want to store a nice simple list of just the nodes themselves, right? So you want to have a list of pointers to the nodes. Okay, well what you do is you create a list of weak pointers to the nodes, because you don't want that list of weak pointers to keep the nodes alive, potentially. If the nodes are going to get deleted, they're going to get deleted. You're just keeping a nice list of it. And then every time someone wants you to print out the nodes, you just loop through that list, and then you try and get a lock on everything. And if any of them are null, you know that they've been deleted since then. So it's just a big shared ownership model. And again, like most times I've seen people working with stuff, they've just been using unique pointers because it's a fairly simple idea. You're creating a heap object and you don't want it you want it to be managed. Shared pointers are, I think, more obscure. I think Chris used to say a lot that people overuse shared pointers quite a lot, because most of the time people think they don't know what's going to go out of scope first, but they actually do if they like paid attention to it. And it gets really confusing, as some of you are experiencing. But concurrency would definitely be, I think, the biggest area that this would be noticed in. Because has anyone done operating systems here? No one? Okay, one. Okay. You don't answer yes to anything, you lot. So like, the operating system's a great course, and in that one you kind of do a little bit of concurrency too, and you kind of learn about the biggest problem with concurrency is not that there's code running in parallel, it's the non-deterministic nature of it. It's that you don't know what line of code is going to get executed when. And the non-determinism is kind of what introduces the challenges into the programming, because it's harder to work with. Because like if you have 3 threads all printing numbers from like 1 to 100, the whatever it's called, the thing that the context switcher, is it swapping between those different threads, you don't know what order it's going to do. And your computer does this all the time, right? As I'm running OBS and my text editor and the web browser, there's only so many CPUs and things going on, and it's constantly swapping between them randomly. Like it's an aggressive multitasker, and you don't know what order stuff's going to happen in all the time. So that's really where shared pointers would probably shine the most. Tim says, can you unlock explicitly? I don't know. So Tim's like, do we have to wait for it to go out of scope? Let's check. Maybe you can. Weak pointer. Lock expired. Checks whether the referenced object was already deleted. Yeah, so I mean like this you don't even need to do the like this code here with the y thing, like you can kind of be like if wp.expired. You just read the docs, right? Like if it hasn't expired, then you get a lock on it, then you do something with it. Use count we've seen. Owner before provides owner-based ordering of weak pointers. Checks whether this weak pointer precedes other. I'm not smart enough to interpret that quickly. Yeah, there's a few interesting things here. Swap, yeah, pretty standard stuff. Tim says, also wonder why we need this weak pointer at all. Wouldn't it be more elegant just to be y equals x dot lock? Okay, I see what Tim's saying. Tim's kind of being like, why are we doing all this weak pointer stuff? When we want to create another shared pointer of it, why can't we just say like x dot lock like this? The reason is because the reason a weak pointer exists is because sometimes you might want to store something longer than the shared pointer might exist for. So obviously in this particular scenario, you know that x is still in scope, so it seems really silly to create a weak pointer. And I know this code's quite simple. But again, I don't have a good lot of threading examples for you. But let's imagine here for a second that you went and created like a new thread function and you called it, and what you wanted to do was you wanted to pass in like a new weak pointer to it or something. What this would mean is that like you could go have this function run concurrently for a long time with basically a weak reference to that original piece of memory, this one here, knowing that somewhere further down the line something might go out of scope whilst another piece of code's running. Again, it doesn't seem very intuitive when you look at this really like linearized program. So just imagine things running in parallel, I think would make a lot of the understandings quite more digestible. Weak pointer, yeah, we had a look at that. Okay, when to use which? Unique pointer versus shared pointer. You almost always want a unique pointer over a shared pointer. Use a shared pointer if either the object has multiple owners and you don't know which one will stay around the longest, or you need temporary ownership, which is unlikely. So again, I want you to imagine a lot of that stuff as like fairly academic. Even like that graph example that I gave you earlier, you could still probably just implement that with unique pointers anyway, just by changing how something's defined, like, so point is, when you come around to doing this in assignment 3, and I do remember, I haven't taught this assignment 3 in like a few years, so it's a bit hazy, but we have seen shared pointer examples and we have seen unique pointer examples, and I think both are valid. I'll have to go and double check that, but I do remember that it's like, if students just use unique pointers, their lives are easier, because you're not thinking about all this reference counting, BS. It's just like, yeah, you're just managing heap objects. Okay, examples of smart pointer usages: linked lists, doubly linked lists, trees, graphs. I mean, yeah, bit of a silly slide, like smart pointers, sorry. All of these things would be using smart pointers where they can, because it's just easier. Like, you would pretty much use a smart pointer for virtually every single malloc piece of memory you can, so that you have one less thing to stress about. Okay, yeah, leak freedom in C++. This is a little poster thing that we've included in the slides. Basically, what it's saying is you should basically always be able to solve problems by creating stack objects. On the very few times that you can't do that, you can create heap objects, but make sure you wrap them in a unique pointer. And on the very few times that you need to copy that unique pointer or have observers, and you think the observers might need to outlive the unique pointer and you can't manage that, concurrency or something, then you look at shared pointers. So imagine it as like an aggressive funnel inwards, where like 80% of the time it's like stack, that 20% of the time heap. Okay, 80% of the heap time, unique pointers, 20% of the time, shared pointers. Stack unwinding. Okay, this gets towards the end of what we're talking about today. So stack unwinding is a concept that relates to exceptions. Now, the funny thing about exceptions and why some people might not like them is because they really break the rules of programming. Everything we do in programming, if statements, else statements, while loops, whatever, it follows a really nice, elegant flow through the program, right? You like come in, you do stuff, you go back out to where you came from, etc. Exceptions like stop everything. I want you to literally stop executing that function mid-line, cancel everything after it. We're going to jump up functions and aggressively basically jump through the program until someone deals with us, right? That's why they're so great to use, and that's why they're so difficult, is they're difficult to reason with. That's why you probably see things like some of those programs people want to like do formal methods on. I don't know much, but I doubt they have many exceptions in them because they just make reasoning with programming really hard. The thing with stack unwinding, though, is whilst it's popping off the stack, whilst it doesn't execute any code, once it halts and doesn't go any further, it does, however, take things off the stack, and therefore destructors are called on the way out. So if you have a function and you've like added a couple variables on the stack, and what I mean by that is like if you have void hello like this, and you have like int I equals 1 and int j equals 2, and then you like throw a standard exception, it will pop I and j off the stack naturally, right? As it leaves that function. It will clean itself up as it goes. Any resource not managed by destructors won't get freed. This is really important because what this means, as an example, let's imagine I have a standard vector of ints. 1, 2, 3. Now, let's imagine that I go, well, I'm going to make a new little piece of memory here. It's going to be a new int. It's going to be the number 5. I like the number 5. And then I'm going to delete the number 5. And you know what? In between doing that, I'm going to say, you know what? Let's just print out what's at v.at position 6. Okay. This is bad. This is bad because what's going to happen is it's going to execute this line of code. It's going to execute this line of code. We have two stack objects here, v and n. V is a reference, well, v is this stack object here. It is an actual object. The vector is going to contain pointers to heap objects inside of it, but that's all managed behind the stack because the vector is our nice little stack protection. N here is just a pointer. The exception is called because .at triggers an exception. The program halts execution there and immediately starts stack unwinding. It starts trying to pop off the stack until someone handles it. It frees v and n off the stack. As it's freeing v and n, it calls the destructors of v and n. There is no destructor for a pointer, but the destructor for v will go and free all the underlying heap memory. But that's not how the pointer behavior works, right? So what ends up happening as this is popped off the stack, this delete never gets called. Popping this pointer off the stack never calls its delete. So now you've just left yourself with a memory leak because of an exception. So stack unwinding is quite dangerous when it comes to these. There's a lot of reasons not to use new and delete and malloc and free and stuff, right? You get away with it in C again because exceptions aren't really like a big thing in C, C programming is quite simple. So you don't randomly have the code just stop executing and just like shoot stuff off the stack and be like, all right, good luck. Oh, wow, that was a great idea, Hayden, to make that code so small. You're a fucking genius. All right, let me just copy that in. We got 3 examples here. Let me paste them in a better file. And let me separate them by a nice little line. All right. So, first example. I've got a function that simply throws a runtime error. Great. This is one I showed you before. You have a main function, you call g, a runtime error is thrown, stack unwinding begins. Bad. All right, now you've got another example here. This is also bad. I don't actually know why that one's there. Let's ignore the middle one. But this is how you would go around fixing it, right? You would apply what we've learned about unique pointers at the bottom here. Let me just get rid of this middle one for a second. Because if you look at it, the top one will have a memory leak. Obviously, the program ends straight away, so it's not going to be a big problem. But imagine this is a big program, we'd have a problem. But the bottom one, because we simply made this value with a make unique and the heap object got wrapped in a unique pointer, when g was called, what happens? Stack unwinding begins, so the pointer name gets popped off the stack. the unique pointer gets popped off the stack. And what does a unique pointer love to do when it goes out of scope? Free its underlying heap resource, so there's no memory leak because your unique pointer dealt with that. So this is why it's really important, because I think I've talked to students in the past where they think, oh, well, smart pointers, sure, they're cool, but I'm smart too, yo, kind of thing. And I can manage it myself. I can track, and I know how to delete something I free. I can take responsibility for it. And it's like, yes, true, but are you then going to make sure that all the code you call between the new and the delete is no except, or that it's appropriately wrapped in tries and excepts, and that, you know what I mean? Like, it gets quite deep very quickly. Whereas this just saves a bunch of our pain. So that's what we need to consider with stack unwinding. Okay, during stack unwinding, standard terminate will be called if an exception leaves a destructor. If an exception leaves a destructor. Yeah, okay. This is kind of unrelated to smart pointers. Basically what this is saying is that we talked about, I don't know why this slide's here actually, to be totally honest. When you write a destructor, you can throw exceptions in the destructor, but they all have to be no throw guarantees. So like a destructor can have an exception in it, but it has to be handled in that. It should never bubble out of the exception, out of the destructor, sorry. And the reason we're saying that is because how C++ is written is that if it detects that there is an exception that bubbled out of a destructor, it will terminate the program on the spot. It is like red flag million times over, kind of like destructors should not be throwing uncaught exceptions. Because if your code has gotten to the point where it is like randomly panicking whilst cleaning up itself, then it's like bad times are ahead. So don't do that. I don't think that's related to, maybe it's related to the next slide and I've just forgotten. So last points here, partial construction. What happens if an exception is thrown halfway through a constructor? Now we've got some other funny what ifs. So I've got myself here a little myInt class. Okay, it takes in an I, sweet. If I is 2, it throws an exception. It's a very prejudicial random class there. Just throws an exception if you try and construct it with a 2. Cool. Then we have an unsafe class here where we're on the wrong screen. Oh, it doesn't seem to like doing the full screen stuff today. Oh, no, it's just frozen, actually. Sorry, guys. Very weird. Should be fine now. Let me just check. Cool. Still come up when I full screen it? Oh, it's a bit cut off. Okay, anyway. So partial construction. If we look here, we have an unsafe class. And what happens with the unsafe class is we pass in 2 ints, A and B. And then what we do is we try and create heap objects for that A and B. And we try and track them here, and we have a destructor that deletes them, right? We basically created a little smart pointer, little smart pair pointer, if you will, right? Takes in 2 objects, puts it in the heap, tracks it, so we can pop it off. We can pop unsafe class off the stack, and it will be all okay. However, one problem we have, and this example's real trite, but I love it, is there is a C++ standard comment that says an object that is partially constructed or partially destroyed will have destructors executed for all of its fully constructed sub-objects. All right. A destructor is not called for an object that was partially constructed. This is problematic for us too, because if you pay real close attention, we've just tried to create an unsafe class where we passed in a 1 and a 2. Partial construction bad. Yep. So we try and pass in a 1 and a 2. Well, what happens here? Unsafe class takes in the 1 and the 2. It tries to malloc the 1. Well, it doesn't malloc, sorry. It mallocs myInt with a 1, which succeeds. So we create a class containing a 1, put it on the heap. Then it tries to create another myInt class with the 2. Oh my god, our random class that's really prejudiced against 2s threw an exception while construction was happening. Okay? Well, what happens then? In the middle of unsafe classes construction, an exception was thrown by something inside of it, and it wasn't caught by anyone. So what happens then? Well, an object that is partially constructed will have the destructors. Yeah, what it's basically saying here is like, if this gets halfway through construction and it doesn't succeed, it kind of aborts itself, just like gives up on it. But the tricky part here is a destructor is not called for an object that was partially constructed. So what it's saying is that we got halfway through constructing this object and then it didn't continue, but this destructor was never called, because destructors are only called on a class, on an object, I should say, if its constructor finished, right? So destructors only called on class objects where its constructor finished. If its constructor fails halfway through, the destructor is never called. Now that becomes problematic here, because now you think, oh, I'm a genius, I've written myself a little safe class, but what actually happened was that the new malloc this myInt class, so this one's been malloc here, this one failed the malloc because an exception was thrown, but the destructor was never called, so we actually malloc this one here, and the whole object was kind of thrown in the bin, but we never freed it, right? Are you kind of following how that never got freed? Running out of steam. So this got malloced, never freed, because this crashed, this had an exception, and it was like, oh, we didn't finish constructing, better not call the destructor. So we got to be really careful of partial construction. However, the great thing about all the stuff we've been talking about, you can just use smart pointers to fix it. So you could actually solve this problem with these smart pointers, because what this would do is if you partially constructed this and an exception was thrown on this line, because this unique pointer is a stack object, as it is kind of destroying the class itself, it frees the underlying resource. Because what I'm saying that when an object is partially constructed and there's an exception, it still has to get stuff off the stack, right? Everything off the stack always gets managed. If the stack wasn't functioning, the program wouldn't work. So, because how does a class work? Well, a class starts getting constructed and it creates the stack objects and it starts preparing them. Okay, so then it fails. Cool. Now I have to remove my stack objects, but it's never going to call the destructor. So we don't have a destructor, which is a great reminder that in general, destructors are evil. If you're writing your own destructor, you've got to be really careful. You need to really make sure you're writing it for a good purpose, because this one, like this example, felt like a good purpose. You were like, oh, I'm writing a class that manages things, it does a good thing, but partial construction was a problem, and the unique pointer would have saved you there. So that's important. You could obviously put try and catches in the constructors. However, where you got to be careful is like some things you just can't try catch your way around. Like there's going to be cases where data's just not valid and there's no reasonable exception for it. Like some constructors will just always have some kind of exception case that you have to deal with. Object 2 is, an object managing a resource should initialize the resource last. This is also like another good example of like when we talk about RAII, it's like when you initialize something is when you should wrap it in a resource straight away as close as possible. Yeah. Could the smart pointer class constructor throw an exception? It's a good question. I don't know. I imagine that it's simple enough. It's the right kind of like way of thinking, because like, maybe it could. And what did I click on? Unique pointer, constructor. No except, no except. So it looks like it can't, which is good. But yeah, if it did, it would be problematic for sure. And I'm sure there's things out there that might throw it as well. Yeah, that's good that it's no except. Good question. Oh, okay. Any questions about any of this? We're kind of wrapped up for tonight now, so it's not too much. We took that pretty slowly and stepped through it. Yep. Is there any difference in performance between raw pointers and smart pointers? Yes, there's going to be, because obviously it's got to like construct an object and put it on the stack. The main, I guess, again, design ethos of C++ is that whole notion of lightweight abstractions, not free abstractions. So like the point is that, there's managing the pointers yourself, and then there's like Java managing the pointers, and Java's going to be like really heavy when it does all this like looking after pointers, whereas C++ is just meant to be like a little penalty. Like all the penalty is like creating a couple of stack objects. So it would definitely be like finitely slower. I think it's one of those things where there's probably an extremely rare number of situations where someone would be writing code where like that little 1% of performance needed would like exceed the headache of debugging and whatnot. But yeah, definitely. Same with like a vector. Like a standard vector is slower than a C-style array finitely. It's just not much slower. But if you compare like a C-style array to like a Python array is like 100 times slower. So yeah, it's just a lightweight abstraction. Cool. Excellent. All good? Okay. Any other questions? All right, be free. Have a good evening. I'll see you on Wednesday for those who come and aren't kind of panicking on their assignment. But it sounds like most of you are on top of it, so should be okay.